Hey guys, and welcome to this video on 8.7 vectors. There's going to be several different videos on vectors because there's a lot of different things that we're going to learn about vectors. So I've split this section up into 3 different videos. So this is the first video, an introduction to vectors. Make sure that you have your geometry notes out and that you put the title at the top of the page, 8.7 vectors. All right, let's get started. Did you know that people actually use vectors in everyday life? Meteorologists use vectors to represent weather patterns. If you look at the picture on the screen right now, you can kind of see one example of when they would do that. For example, wind vectors are used to indicate wind direction and speed. So if you someday decide to become a meteorologist, you will use vectors in your everyday life. They're of course used for other things as well, but meteorology is probably one of the most common, most popular uses of vectors in the real world. But what exactly is a vector? We're going to kind of talk about that in this first part of the video. There are 3 different vocabulary words for us to talk about: vector, magnitude, and direction. A vector is something that has both magnitude and direction. So to understand what a vector is, we have to understand what magnitude is, and we have to understand what direction is. So first, let's talk about magnitude. Magnitude is the size that something is. But usually in math, when we talk about size, we might say, oh, that table is 1 meter long. And that's usually what we mean in math when we talk about size. In this case, it's going to be a little bit different because size can also be a scalar, which an example of a scalar is 5 miles per hour. That entire phrase, 5 miles per hour, that's actually a size of something. It's not just the 5 miles that's the size, it's actually the 5 miles per hour that's the size. Kind of like speed a little bit too. So magnitude is the size of something, but size can also be like 5 miles per hour, that's a size. Now let's talk about what direction is. Direction's a little bit easier because direction's a little bit more straightforward. Direction is going to be measured in degrees. We have 2 pictures here at the bottom of the screen that both talk about direction. This first picture here on the left is saying the direction of, and then that little symbol is a vector. So the direction of vector A is 30 degrees relative to the horizontal. So if we just had a regular horizontal line and we used a protractor and we measured out a 30-degree angle, that vector, vector A, would be 30 degrees. That would be the direction of the vector. You could say 30 degrees relative to the horizontal line. There's one more way that you can also measure direction. It's still using degrees, but instead of marking it in proportion to the horizontal line, you're going to instead use the vertical line, and we're going to call it the north-south line. So you could say the direction of vector A is 60 degrees east of north. If the vector was just straight north, it would just go from the origin all the way up to the end. That would just be like a vector going straight north. But the vector that we see here in the picture is tilted diagonally. It is 60 degrees east of north. So you can use either of those 2 ways to describe the direction of a vector. Both of them are going to use degrees. One of the ways is going to use degrees in relation to a horizontal line, and the other way is going to use degrees in relation to north, south, east, and west. So we've talked about direction just now. We talked about magnitude before. Let's put both of those things together and talk about a vector. So a vector is kind of like a line, but it's not really a line, it's not really a line segment. It's more like a ray than it is anything else. And a vector is kind of like a ray that has a starting point and an ending point, and it has a magnitude and it has a direction. So a vector, in order for it to be a vector, would need to include both a size, like you would need to say, oh, this vector is 5 miles per hour, or this vector is 2 meters per second. And you would need to have a direction for the vector as well. You could say, oh, that vector is 25 degrees relative to the horizontal. Or you could say, oh, that vector is 10 degrees west of north. So in order for it to be a vector, it has to have two things. It has to have a magnitude, and it has to have a direction. Here's what we're going to do now. We're going to take a look at some example problems. And the textbook is going to give us an example. They're going to say, all right, here's a vector. This is the magnitude of the vector. This is the direction of the vector. Go ahead and try to draw the vector. So they're going to give us those two pieces of information that we need. They're going to give us the magnitude, and they're going to give us the direction, and they're going to ask us to draw what it would look like. Now, don't worry, because we're going to do a couple examples together, and then you guys are going to try this on your own. Let's take a look at the first problem. Oh, I almost forgot to tell you really quick. Okay, so there's one more thing we have to talk about, and that is how to actually write down and label a vector. So you can see there's a couple different symbols on this paper. I'm going to zoom in here. These are the three different ways that you can label a vector. So you can call a vector like vector AB. This would be the starting point of the vector, the A, and then the B would be like the ending point of the vector. But a vector is different than a ray. A ray is just like a line that starts somewhere and then it goes forever and ever in one direction. So a vector is not a ray, so you can't label it the same way that you would label a ray. Do you know what the difference is? If you can look at this little symbol here, notice that the arrow only has one side of it instead of two sides of the arrow, and it's kind of curved as well. So if you can see, it kind of curves right here. So it's like a straight line and then it curves backwards like that. So that's the symbol for a vector. So you can call something vector AB. You can also call it just vector A if it's labeled with an A, like the one in the picture right here is labeled with an A, so you can call this vector A. Or if you have a computer and you can bold your font, then sometimes you will also see a vector denoted this way with a bold letter A. So those are the three different ways that you can write down a vector. All right, so now that we talked about that, now we can get started with the example problems. All right, guys, so here's the first problem. Let's figure out how to draw this vector. Remember, a vector has two things. It has magnitude and it has direction. They've told us that the magnitude of this vector is 15 miles per hour. That is the magnitude. And they've told us that the direction of the vector is 140 degrees to the horizontal. That's the direction. We need to use these two pieces of information to draw the vector. So let's start by talking about the magnitude. How can I draw 15 miles per hour? Give you a hint. You can't. You can't really draw 15 miles per hour. So what they do in situations like this is they just draw a line and they're like, look, that line is 15 miles per hour. So it doesn't actually matter how big you make the line. You can make it that big, or you can make it this big, or you can make it this big. And then you just say, like you put a little note on your paper, you're like, there, that line is 15 miles per hour. So it doesn't really matter how big you make it. Now, if you want to get fancy, you can use a different scale. Rather than saying, oh, that line is 15 miles per hour, you could say, well, let's use this line that I'm going to circle right now. And let's say that on my paper, if I split this line into 3 sections here, the way that I have it drawn, each one of those 3 sections happens to be 1 inch long. So total on my paper, if I was going to take a ruler right now, that line that I circled, that's going to be 3 inches. So I could include a scale, and my scale would say 1 inch is going to equal 5 miles per hour. Then when you have the whole thing, now it's 15 miles per hour. But there's no magic way to do it. There's no formula way to do it. You basically just draw a line, and then you can kind of create whatever scale you want to create. You can say 1 inch is 5 miles per hour. Or if you're doing it on a huge whiteboard, you could say 10 inches is equal to 5 miles per hour. Or if you're doing it on a really tiny little piece of paper, you could say 1 centimeter is equal to 5 miles per hour. But you don't actually have to use that scale. You could make up your own scale. So for magnitude, you basically just draw the line and you label it however you want to label it. You just have to make sure that when you label it, it's going to end up being the 15 miles per hour. Okay, now let's talk about the direction. Is the line that I drew and circled 140 degrees to the horizontal? No, it's definitely not. So we're going to need to change it, and we're going to need to figure out how to draw a line that's 140 degrees to the horizontal. Now, if you look at the directions at the top, it says use a ruler and a protractor to draw each vector. So technically we're supposed to have a protractor here. A protractor, that's like either the circular thing or the half circular thing that allows you to measure the degree measurement of an angle. Now, I can't really do one on this video very easily for you, so we're kind of going to estimate 140 degrees. Now, I know that this is 90 degrees, and I know that the whole thing is 180 degrees. So 140 degrees is almost in between the 90 degrees and the 180 degrees. It's a little bit closer to the 180. So my line is going to be almost in the middle, but maybe a little bit closer to the 180. So I'm going to estimate, and I'm going to draw this line here. I'm going to pretend that that line is 140 degrees to the horizontal. And if I could include a protractor in this video, then I would make it a little bit more exact. But for now, I'm just going to say, you know what, that's 140 degrees. In order to do a vector, we have to make sure that it's 140 degrees, and we have to make sure that it's 15 miles per hour. We have to follow the direction, and we have to follow the magnitude. But remember what I said about the magnitude? It doesn't really matter like how you draw the magnitude. I'm just going to leave my line here, and I'm going to say, oh look, that vector is 15 miles per hour. If I want to get fancy, I can include some type of scale. I can say maybe this is equal to 1 inch. I'm just going to pretend, because this is a video. So I'm going to say this is equal to 1 inch. So my scale is going to be that 1 inch is going to equal 5 miles per hour. So the entire vector that I drew is 3 inches long. So therefore, it is 15 miles per hour. So I'm going to highlight my final answer. My final answer is this vector that I have highlighted. I made sure that the magnitude was 15 miles per hour, and I made sure that the direction was 140 degrees to the horizontal. I'm going to zoom out and show you the pretty little vector that the textbook drew for this problem. This is what the textbook's vector looks like. You can see it kind of has the same degree as mine, 140 degrees, kind of facing the same way. And they chose their scale to be 1 centimeter is equal to 5 miles per hour. All right, let's do one more example together before you try one on your own. They want us to draw vector C, 55 pounds of force at 55 degrees west of south. It's actually going to be easiest for us to begin using the directional part of the vector. So 55 degrees west of south. if I have a compass here, this is going to be north, south, west over here, and east over here. So if it's west of south, it means that we're starting with the south, we're starting here, and then when we go west, we're going to make our vector go that way, kind of. So 55 degrees west of south. 45 degrees is going to be exactly in between the west and the south, because I know this is a 90-degree angle, so 45 is going to be exactly half of it. So it's a little bit more than halfway from the south to the west. So this right here is probably a little bit more than halfway. This would be 55 degrees west of south. So I'm going to redraw that right here. This vector that I have just drawn is about 55 degrees west of south. I'm going to do a little dotted line here, and I'm going to show that this is south. And so I'm going to label this right here as being 55 degrees. So that vector is 55 degrees west of south. Now the magnitude, that's the easy part. That's the part that you just get to make up. And the magnitude says 55 pounds of force. Well, guess what an easy way to do it is? You can just say this whole vector that I have just drawn here represents 55 pounds of force. Another way that you can do it if you want to use a scale is, let's see, 55 can be divided by 5. So I could try to draw a scale that's about 1/5 the size of my vector. And I might say that's equal to about a centimeter. So I could say that 1 centimeter is going to equal 11 pounds of force, because my vector would be 5 centimeters long total, so therefore it would be 55 pounds of force total. So you could use that same scale that I did. The textbook decided to use a different scale for this problem. This is the scale that the textbook decided to use for the 55 pounds of force, 55 degrees west of south. With their scale, they're choosing to say 1 inch is equal to 25 pounds. So their line is a little bit more than 2 inches long. A little bit more than 50 pounds, it would be 55 pounds. So that's what the vector should look like. All right, now let's try 2 problems on our own. These are the 2 problems for you guys to try. Go ahead and pause the video now. Draw what you think they should look like in your notebook. And then after you're done, you can keep watching the video and you can compare what you've drawn to what the answer is, and you can see if they kind of look similar. Boom, there's my 2 answers. All right, so this first one, we're going to say it's 40 feet per second, and it's supposed to be 35 degrees to the horizontal. So this little dotted line that I'm drawing right now, this is the horizontal, and we're going to say that this is about 35 degrees. You can use a protractor in order to draw it properly, or I estimated, I know that 90 degrees looks like this, and I know that 45 is exactly half of 90, so I did a little bit less than the 45. All right, and for part B, it says 85 degrees east of north. I'm going to again draw a dotted line, but this time I'm going to draw it, this is the north dotted line, and if it's east of north, east is going to be this way. So I measured 85 degrees this way. I know that 85 degrees is just 5 degrees less than 90. So if it said 90 degrees east of north, that would be perfectly straight this way. And so I tried to draw it like 5 degrees up from that. So this is 85 degrees east of north. The degree part, the direction part of the vector, that's really the most important part to make sure you're drawing accurately, because the magnitude, you can literally just label it and say, oh look, that's 40 feet per second, or oh, that's 12 kilometers per hour. And that's what I've done for both of these. I'm going to say that my first vector, the magnitude is 40 feet per second, and the second vector, the magnitude is 12 kilometers per hour. As long as yours look kind of similar to this, great job. Okay, so I know that that's kind of already been a lot of new information, but there's actually one more thing in this video, but only one more thing. The next thing is we're actually going to learn how to add vectors together or subtract vectors from each other. Here's how to do that. When you add vectors together, that's technically called finding the resultant, new vocab word. So if the directions say, find the resultant of these two vectors, they're really asking for you to add the vectors to do that. Now there's a couple different methods that you can follow in order to add vectors. When you add vectors, there's no math that you're doing because a vector does not have a number associated with it. You're really just merging two pictures and making them one picture. The first way that you can do that is you can use the parallelogram method shown here on the left. According to the parallelogram method, you would, step 1, translate vector B so that the tail, that's kind of like the starting point of vector B, touches the tail or the starting point of vector A. So you take the two vectors and you make sure that their starting points are touching each other. Then you pretend like vector A and vector B are two sides of a parallelogram. Remember how to draw a parallelogram? It's kind of like drawing a rectangle. It's similar. The sides have to be parallel and they have to be the same length. So on the top here, they've kind of drawn the other side of the parallelogram. And on the side, they've drawn the other side of the parallelogram. After you have completed the parallelogram, the resultant vector is going to be this vector in the middle. So this vector in green, it's going to have the tail right here, and it's going to have the final point where the arrow is. That is the answer. So the answer is a picture. And that's what the picture should look like, and that's how you can draw the picture using the parallelogram method. So again, just to recap, the parallelogram method, take the two vectors, draw them so that their initial points are touching, and then complete the parallelogram, and the diagonal that you can draw in the parallelogram, that diagonal is the answer. Now there's another method that you can use if you would prefer a different method. It's the triangle method. It's basically the exact same thing. You're going to get the same answer, but instead of drawing all four sides of a parallelogram, notice in the triangle method, they have just drawn two of the sides. They started with vector A. This was the first one that they drew here. And after they drew vector A, then they added vector B to their drawing so that the initial starting point of vector B, right here, is going to be touching the final point of vector A. And then they drew vector B right here. After they drew those two vectors touching in that way, then they created the resultant vector by connecting the initial point of A to the final point of B, and the vector that they drew there, that was the resultant vector. So you can choose either way. You can choose the parallelogram way, or you can choose the triangle way. It doesn't matter how you do it. If you follow one of those two ways, you're still going to get the same answer for your resultant vector. Let's do a couple example problems where we're going to try to add vectors together. All right, so we're going to try this example problem here. If you want to pause the video, you can go ahead and try it on your own. See if you can follow one of the two methods to add these vectors together. And then I'm going to provide a full explanation of how you can add these vectors together. But if you want to try it on your own, go ahead and you guys can hit pause. All right, when I add the vectors together, I do the parallelogram method. So I'm going to copy vector C as best I can. That's what vector C looks like. Then I'm going to copy vector D, and I'm going to make their initial points touch. So this is what vector D looks like, and their initial points are touching right down there. And now, according to the parallelogram method, I'm going to complete a parallelogram that's going to have this side the same and this side the same, parallel to the other. And then I'm going to draw the resultant vector as the diagonal of the parallelogram right here. That green vector, that is my final answer. So that is the sum of vector C and vector D. We're going to use the same picture now to do two last problems, and that's going to be it for this video. We just have two problems left. We just did addition, now we're going to talk about subtraction. First, let's see if we can figure out how to take vector C and subtract vector D. So we want to subtract these ones. If you are subtracting, you have to take whatever vector you are subtracting, in this case we're subtracting D, and you have to flip it around so that it has the same magnitude, but it has the opposite direction. So the tail end, the initial part, and the starting part, we're going to flip those around. So instead of looking like this, D is actually going to look like this. It's going to be the same magnitude, so that means the same size, but now the initial point and the ending point, those are going to be flipped around. So now we're going to add C to negative D, or the inverse of D, or the opposite of D. We already know how to add vectors. We just take vector C and we take what is now the opposite of vector D, and we connect using the parallelogram method. We connect those initial points together, and then we complete the parallelogram. So complete the parallelogram here, and complete the parallelogram here. And then we draw the diagonal of the parallelogram. That's what the final answer should look like. So again, just to recap, when we subtracted, the first thing that we did is we took vector D right here, and we just changed the picture to make the arrow go on the other side. And then once we changed the picture, then we forgot that this one even existed, and we just used this one to add it to what C already was. So when you do subtraction, after you flip the vector, then you pretend like you're doing addition. All right, we're going to do one last problem. We're going to do vector D minus vector C. So instead of flipping D around, now we're going to flip C around. If you want to pause the video, you can try it on your own. And then once you unpause it, I'm going to give a full explanation of how to do vector D minus vector C. Okay, so when we start with the D minus the C, we're going to keep the D the same. This is vector D. And then when we subtract C, now we're going to reverse the direction. So same magnitude, but direction are reversed. And now that we did that, now we can just add them together like as if they were both positive, because now we've already done the reverse flipping for the C vector. So in order to add them together, I'm going to take D and put that right here. And then I'm going to take C, and remember the initial point here and the initial point here, those have to touch. So this initial point has to touch the initial point for the C. And now according to the parallelogram method, now I can add this side of the parallelogram, and I can add this side of the parallelogram, and now I can draw the resultant vector, and that's going to be my final answer. So that green one, that's going to be D minus C. All right, that's it for this video. Make sure to take a picture of your notes and submit them on Canvas. Thanks, guys.